In this video, we're going to talk about computing area. We've already done this to some extent because we know that if f is greater than or equal to 0 for all x on an interval, let's say from a to b, then the area under the curve is equal to a for area is equal to the definite integral from a to b of f of x dx. This is a statement about area underneath curves that are non-negative. That is, the curve doesn't go below the x-axis. So we're looking at the area from A to B, like so. And this area is given by a definite integral. We also know that if the function is negative, if it's below the x-axis, then the definite integral will give us the opposite of area. Well, in this video, we're going to speak more generally, not about area underneath a curve, but area between two curves. So let's talk about the area between two curves. Suppose f is bigger than or equal to g on some interval. So let's say for all x in the interval. Let's just call it a to b again. Then the area between the curves, between y equals f of x and y equals g of x, from x equals a to x equals b, is given by the formula a for area is the definite integral from a to b of the bigger function minus the smaller function. It might help if we draw a picture. Let's suppose that we have an xy plane here, like this. And we have two functions. One is f and one is g. We don't know anything about them, except that f is bigger than g. So if g is down here, then we know that f has to be taller, although we don't know anything else about it. The region in question is the region between A and B, like this. So we're interested in finding the area between the two curves from x equals A to x equals B. So this is the region here that I'm shading in. So the formula tells us that in order to determine this area, it's enough to integrate the difference between f and g. In this particular picture, both f and g are positive. And, excuse me, let me redo that. There we are. In this particular picture, both f and g are non-negative. So in this case, in the case that f is greater than g and g is non-negative, and so if g is non-negative and f is bigger, then f must be non-negative too, then we can see that the formula is correct. Why is that? If we look at the integral from a to b of the difference between f and g, so f of x minus g of x dx, we can write this integral of differences as the difference of the integrals. So the integral of f from a to b minus the integral from a to b of g. So the integral of the difference is the difference of the integrals. But this first integral, the integral of f, is the area under the curve y equals f of x. And the second integral is the area under y equals g of x. So what you're looking at here is first the area of the whole region, the area underneath f. So that's the area between a and b under f. So that's the blue region plus this little bit extra. But that little bit extra is exactly the area underneath g. So if you start with the area underneath f, which is a very much larger region, and then you subtract the area of the region under g, you're left with the area of the region between the two. So we can see geometrically that this formula is correct when you're dealing with functions which are both non-negative. However, what's interesting about this, so fact, we do not need f of x greater than 0 or g of x greater than or equal to 0 for all x for this to be true, for this formula to be true. Now when I say this formula, I'm talking about this formula right there. So even if f and g are negative sometimes, or if g is negative and f is positive sometimes, it doesn't matter, the same formula works. As long as f is bigger than g, you always need the bigger function to go on top. That's very important. So the larger function must be first, must go first. Now why is this true? Well, imagine that you have some region, and we don't need to draw in the x-axis here. Let's say that this is the y-axis, and we have two functions like so. The top one is y equals f of x, and the bottom one is y equals g of x. Now, if you want there to be an x-axis, we can draw one in, but it doesn't have to be anywhere in particular. We can just draw it right here, for example. So this can be our x-axis. So you can see that g is negative, f is sometimes negative, but sometimes positive. And suppose we wanted to find the area between a and b. Let's put a here, and let's put b over here. So we want to find this area between these two regions. So we can shade it in, although perhaps I'll make my marker a little bit bigger because this region is a bit bigger than the region we looked at before. So we just fill it in, and we see that it's sometimes above the x-axis, sometimes below. Now why would it be that the area of this region is given by that formula? Well, suppose that we have an x value. Let's say this x value right here. What I'm going to do is I'm going to draw a very small rectangle. It's going to be a rectangle from the top, y equals f of x, to the bottom, y equals g of x. So I'm going to draw a very small rectangle. So this is a very, let's say, narrow rectangle. Let's say the width of it is delta x. In mathematics, when you see delta x, that usually means a small change in x. So here the width is delta x. And as you can see, delta x is very small. This rectangle is so narrow, it looks like a straight line, or maybe not a straight line because I didn't draw it as a straight line, but it looks very narrow, almost a straight line. So what we want to do is we want to compute the area of this narrow rectangle. So the area of the narrow rectangle, that's supposed to be an n at the start there, the area of the narrow rectangle is going to be the height, let me call it h for height, times delta x. So in that case, this height here is h. And how do we determine h? Well, h is going to be the distance between this point on y equals f of x and this point on y equals g of x. Now they have the same y value, so if you want to compute the distance between them, you just have to compute the difference between their x values. So it's going to be the absolute value of f of x minus g of x, delta x. This is why it's important to know which function is on top, because you're measuring the distance between these 2 points, but they have the same y value. So that means the distance between those 2 points is just going to be the difference in the x values, which is this quantity right there. It's an absolute value, but we know that f is bigger. We know that f is bigger. We know f of x is bigger than g of x. So that means the absolute value of f of x minus g of x is actually just equal to f of x minus g of x. This is our value h. Notice it depends on x. So really, this h here is really a function of x. So this h is a function of x. So now we see that the area of the narrow rectangle is h. Well, let's just write h delta x. But this is f of x minus g of x dx. Not dx. I'm getting a little ahead of myself. Delta x. So suppose I want to compute the area of the entire region. Well, we can estimate the area of the region by dividing it up into a bunch of rectangles. So imagine for every single x starting at A and going to B, you have a small narrow rectangle. And the height of that rectangle is going to be your h times the width, which is delta x. But we're imagining that these rectangles are so narrow that there's basically just one point in them. And so this h is going to just be this difference between f of x minus g of x. So if we think about this as a limit, as delta x goes to 0, then this becomes a definite integral from a to b, h of x, delta x. But we know what this h of x is. It's f minus g. So that tells us that the area is equal to the integral from a to b of f minus g dx. So it doesn't matter if f and g are positive or negative. The only thing that matters is that f needs to be bigger than g. We need f bigger than or possibly equal to g. Because as long as f is bigger than g, this quantity, f minus g, gives us the height of this narrow rectangle that we see here, this very narrow rectangle. So when we write this out, this is a Riemann sum, and we're not really doing it for every x. We're doing it for so many x's that it's hard to write down. That's why we use summation notation. But when we compute the limit as delta x goes to 0, we basically have a rectangle for each individual x. That you can think of it as being infinitely narrow. This shouldn't be a delta x anymore. Once you compute the limit, you have a dx there. So as delta x goes to 0, you end up with an integral that has a dx. But the basic principle here is that you want to imagine that for each x, for every single x, you have a rectangle which is infinitely narrow, and so narrow that there's only one point in it, and it's that x. And so the height of that infinitely narrow rectangle is h of x, and the width is delta x. So this h of x times d of x, it's not really the area of a rectangle, but conceptually you want to think about it as the area of an infinitely narrow rectangle. The idea is it's a rectangle that has only one thing in it, x. And so the width is infinitely narrow, dx, times the height, which is the difference between f and g. And that gives us our area. So there is a basic principle here. So a basic principle of area. If you have a region, a two-dimensional region, a 2D region in the xy plane, between x equals a and x equals b, and if the cross sections, let's say if the cross section at any x has length, we were calling it h because it was representing the height of a rectangle, but let's just call it length L. If the cross section at any x has length L, which depends on x, for each x in this interval between a and b, then the area of the region is a for area, the definite integral from a to b, that's supposed to be a b, L of x dx, which is the same basic idea that we saw earlier. So if you have some region, let's just draw an x-axis here. If you have some region, whatever the shape, and it starts at x equals a over here, and it ends at x equals b over here, and you want to compute the area, suppose that you know for each x what the cross-sectional length is. So for each x, you look at a vertical cross-section, and suppose you know that the length is L of x. We just call it L of x because it's a length L that depends on x. If I choose an x over here, I'm going to have a much smaller length. If I choose an x in the middle, it's going to be a bit larger for this example. So the idea here is that the cross-sectional length is L of x. And I want to have one of these for every single x. And then I add them together to get the area of the whole region. So the length is L of x. And then we add them all together. Now there are uncountably many of these things. So when you add them all together, it gives you a solid two-dimensional region. And the area is given by this integral. We can think of this in terms of Riemann sums, just like we did earlier. You can imagine that you start with a very narrow rectangle. So the area is approximately equal to the sum of L of x delta x for a bunch of these x's between a and b. And then you compute the limit as delta x goes to 0, and this becomes a definite integral. The smallest x is a, the largest x is b, and you're integrating L of x, and then the delta x becomes a dx. So this is a basic principle of area which is really at play here. And you don't necessarily need to have functions f and g for this to work, although it does work if you have functions f and g. But you can have a shape like this. As long as you know what the cross-sectional lengths are, you can compute the area. Let's check this. Let's check this formula for a geometric object with known area, just to get a feel for how this works. So, as an example, suppose you start with a triangle. Suppose, let's make it easy, a right triangle has base B and altitude A. So we can draw a right triangle. So we want it to have base B and altitude A. So the altitude is here, A, and the base is B. We know this information because it's given to us. It's a right triangle. So we also know the area. The area is 1/2 the base times the altitude. So the question is, can we use this method, this basic principle of area, to compute the area of this triangle? So what I'm going to do is I'm going to put it on an x-axis. Let me just copy and paste it. Copy, paste. So that way we can be sure we have the same one. There we are. Let me get rid of that. So we know that the base is B, so this length right there is B. And we know that the altitude is A, so that means this is A here. And now you can see what I've done here is I've drawn a rectangle with sides of length B and A. And of course the triangle is half of that, so that's how we know that the formula is correct. But let's use this basic principle of area to compute the area, just so we know how it works. So for every x, I'm going to draw a cross-sectional line. And what I want to do is I want to figure out what this L is, this length, in terms of x. How am I going to do that? Well, if you stare at the picture a little bit, you might notice that we have two right triangles. One is this right triangle that we started with, but we have a smaller one right here. Let me just shade it in so, well, I don't need that large size anymore. Let's just shade it in like this. There we are. So now we have our original triangle, but we also have the smaller blue one. These are similar triangles because they're both right triangles, and they both share this angle at the origin. So if they have two angles in common, then their third angle must be also the same, because all triangles have angles that add up to 180 degrees, at least in Euclidean geometry. So if these triangles are similar, that means the ratio of corresponding sides is equal. So if I measure A to L, that must be the same as B to X, because the base of this small triangle is X. Because X tells me how far away I am from the origin in the X direction. So I know that this length right here is X. That's the base of my small triangle. So the altitude of my big triangle to the altitude of my small triangle must be equal to the base of my big triangle to the base of my small triangle. So what I'm going to do now is I'm going to solve for L in terms of X. So I can cross multiply. AX equals B times L. So divide by B. You have AX over B is equal to L. This is our altitude. So that's the length of our cross section. So the area is equal to the integral from 0 to B of L of x dx, but we know what L is, so it's the integral from 0 to B of AX over B dx. Now a and b are constants, so we can just pull those out. A over b times the integral from 0 to b x dx. This is a definite integral that we know how to compute. So we have a over b times x squared over 2, just using the power rule, from 0 to b. And what is that? That's a over b times b squared over 2 minus 0 squared over 2. So what does that give us? That gives us that the area is equal to a over b times b squared over 2, and this b in the denominator cancels with one of those b's in the numerator, and we have ab over 2. That is 1/2 the base times the altitude. Maybe not written in that way, but it's equal to that. So we can see that this formula does work on this example that we already know. Let's look at an example where we don't know the answer to start with. So example, what is the area between the two curves y equals sine of x and y equals cosine of x from, let's say, x equals 0 to x equals pi? We can graph this region, or at least we can attempt to graph it, because we know what the graphs of sine and cosine look like. We're starting at x equals 0, so sine looks something like that, going from 0 to pi, so this is pi over here. Now, cosine starts at 1. Perhaps I made that a little bit too high. Let's just try that again. There we are. Let's make it look like that. So this is going to be our y equals sine of x. Now what about cosine? Cosine starts at 1 here. So it's going to cross sine of x. And we know where it's going to cross. It's going to cross at pi over 4. So let's try to figure out where. So pi over 2 should be right in the middle here somewhere. That's right about there. So that's pi over 2. So they should cross right about here at pi over 4. We also know that cosine is 0 at pi over 2, and it's also minus 1 at pi. So it's going to be right there. So it's going to look something like this. Well, I kind of missed there. Let's try it again. Let's call that good. Let's say that those two intersect there. That's close enough. Now, we know that they intersect at pi over 4 because we know that sine of pi over 4 is equal to square root of 2 over 2, and cosine of pi over 4 is the same. So the bottom one here, well, it starts out on top, but over here to the right it's on the bottom. Y equals cosine of x. So that's our x-axis. This is minus 1 here. Now what we're interested in is we're interested in the area between these two curves from 0 to pi. So let's shade this in. Well, to the left of pi over 4, cosine is on top. But to the right of pi over 4, sine is on top. Our formula is given in terms of the top function divided minus the bottom function. So the function, which is the top, changes well, not halfway through, but it changes midway through at pi over 4. So let's just remind ourselves. So the area is equal to the integral from a to b of the top function minus the bottom function. Let me just move this so it fits. Bottom function, dx. Now, in this particular case, which function is on top changes halfway through. So it starts out with cosine on top over here. So y equals cosine. But it changes at pi over 4. And then you have sine on top. So what that means is we're going to have to do this in two separate pieces. So let's say the area of the first piece is A, and the area of the second piece is B. Then the total area is going to be equal to A plus B. So we can just compute each one separately. So the area of A is going to be the integral. So we're starting at 0 and we're going to pi over 4. So it's the integral from 0 to pi over 4 of the top function, which in this case is cosine of x, minus the bottom function, which is sine of x, dx. This is a definite integral that we can compute because we know the antiderivatives of cosine and sine. So this is going to be sine of x minus a minus, well, let's write it as minus cosine. There we go, minus a minus cosine of x from 0 to pi over 4. This is really sine of x plus cosine of x from 0 to pi over 4. So this is sine of pi over 4 plus cosine of pi over 4. That's the first part, minus, and then everything evaluated at 0. Now we know what all of these things are because we already talked about how sine of pi over 4 is square root of 2 over 2. Same with cosine of pi over 4. Sine of 0 is 0, and cosine of 0 is 1. So what does that mean? That means you have 2 square roots of 2, well, not 2 square roots of 2. You have square root of 2 over 2. That's half a square root of 2 plus another half of square root of 2. So together that's the square root of 2, and then minus 1. So that's the area of this first region right there. So what about the second region? Well, the second region, that's B. That's the integral from, we're starting at pi over 4, and we're going to pi. But now sine is on top. Sine of x minus cosine of x. You'll notice here that the integrand is the same, except that sine and cosine are reversed. So sine minus cosine is the opposite of cosine minus sine. So if you get these in the wrong order, you'll just end up with a negative sign. And that's fine because really what you're looking at is the absolute value. So if you do one of these integrals and you get a negative, that might mean that you've just flipped the top and the bottom, because you have to have the top function minus the bottom function. But if you do it the reverse, the bottom function minus the top, you just end up with the opposite of this value. And so just get rid of the minus sign, just compute the absolute value. Anyway, that's not going to happen here because we know that sine is on top. So this is going to be equal, well, the antiderivative is the same, it's just now it's got a minus sign. So the antiderivative of sine is minus cosine minus the antiderivative of cosine, which is sine. So now it's minus cosine minus sine from pi over 4 to pi. So this is going to be minus cosine of pi minus sine of pi. And I'm not going to quite have enough room here, so let's just move all of this down like so. Minus, so that's at the upper limit of integration at pi. Now we're going to have minus cosine pi over 4 minus sine of pi over 4. And again, we know what all of these things are. Sine of pi is 0, just like sine of 0 is 0. Cosine of pi is a negative 1. And of course, we already know that cosine of pi over 4 is square root of 2, and same for sine of pi over 4, square root of 2 over 2. So we have a minus 1, minus 0, and then it's minus square root of 2 over 2 minus square root of 2 over 2. So over here you have minus square root of 2, and here you have positive 1. So what you end up with is 1 minus a minus is plus the square root of 2. So if you add a and b together, you're going to have square root of 2 minus 1 plus 1 plus square root of 2. And the 1's cancel, and you end up with square root of 2 plus square root of 2, which is 2 square roots of 2. And that's the area of the region. That's the area of this shaded region between cosine and sine from 0 to pi. Now in this example, we were given the starting point of 0 and the end point of pi, but you're not always given that. Sometimes you have to work it out from the context. So let's look at another example. So for this example, let's ask, what is the area between, let's not say between, let's say, what is the area of the region bounded by y equals the square root of x and y equals, let's say, x squared. Now in this problem, it doesn't tell you what your smallest x value is and what your largest x value is. You have to figure that out. And the way that you figure that out is by looking at the graph. You don't technically need to look at the graph. What you need to know is where the two graphs intersect. So y equals x squared looks something like that. Y equals x squared. And y equals the square root of x looks something like this. Y equals the square root of x. So at some 2 points, they intersect. Now what are those points? Well, in this case, you might be able to work it out, especially since one of them is 0. But the way to work it out is just to ask yourself, at what x value do these two agree? That is, what x value do these have the same y value? If they have the same y value, then they must be equal to each other. So to find the points of intersection, what you need to do is you need to equate the two. So we want to know when x squared is equal to the square root of x. So how do you figure that out? Well, you can square both sides. X to the fourth equals x. Subtract the x. Factor out an x. So, in other words, you have that these two expressions, x squared and the square root of x, are equal if x is equal to 0 or if x cubed is equal to 1. Well, that really means that x is equal to 1. X equals 0 is the first point of intersection. The second point of intersection is 1. We're interested in the area between these two curves. So that's this region right here. We're interested in the area between 0 and 1, between the 2 points of intersection. Well, now we know what our smallest x is and what our largest x is. So the area is equal to the integral from 0 to 1, and we just have to find out which function is on top. Long term, x squared is much bigger, but between 0 and 1, y equals the square root of x is on top, and y equals x squared is on the bottom. That's only between 0 and 1. Once you're bigger than 1, then that changes because the two intersect. X squared long term is much bigger than the square root of x. Now notice I'm only talking about between 0 and 1. That's because y equals the square root of x does not have domain including negative numbers. So y equals x squared shoots off on the other side. But y equals the square root of x is not over there. It does not live over the negative numbers, so the negative numbers are not in its domain. Okay, so the top function between 0 and 1 is the square root of x minus the bottom function, which is x squared dx. Both of these are x to a power because this is x to the 1/2. So we have the integral from 0 to 1 of x to the 1/2 minus x squared dx. So if you integrate these, you'll have x to the 3/2 divided by 3/2 minus x cubed divided by 3. I almost said divided by cubed, but divided by 3 from 0 to 1. So the area is equal to, let's write it like this, 2/3 x to the 3/2 minus 1/3 x cubed from 0 to 1. So this is 2/3 1 to the 3 halves minus 1/3 1 cubed, that's the upper limit, minus the lower limit, 2/3 0 to the 3 halves minus 1/3 0 cubed. All of this stuff with 0 goes away. That's all 0. And on the left here, we have 2/3 times 1 minus 1/3 times 1, which is just 1/3. So the area of this region is 1/3. So far in these examples, we've been using vertical cross-sections. That is, in our example here, we pick an x. So here's an x. And then we determine the length of the line going from the bottom curve to the upper curve. And that's exactly what this is right here. It's the distance between the upper curve and the lower curve at a specific value of x. So it gives us the length of this vertical cross-section. It's also possible to do these with horizontal cross-sections. So we can also use this method with horizontal cross-sections. Let's write it out in generality. So, method for horizontal cross-sections, and it's really no different except horizontal instead of vertical. So suppose, well, let's say if f of y is greater than g of y for all y in some interval, let's call it CD, then the area of the region between x equals f of y and x equals g of y from y equals c to y equals d is given by a for area is the integral from c to d of f of y minus g of y dy. So this is essentially the same formula, we're just changing the roles of x and y. Let's look at a picture so we can see what sort of thing we're looking at here. So the idea is, let's just draw an x-axis and a y-axis, x, y. Now we're looking at functions of y, so we'll have something like this, and something, let's say, like this. Let's continue it down. So the one on the right, this is going to be x equals f of y. The one on the left is x equals g of y. We know that because f is assumed to be bigger than g, and when you're talking about x values, the larger x value is to the right. Now notice that neither of these are functions of x because they don't pass the vertical line test, so they're not functions of x, but they are both functions of y because they pass the horizontal line test. So we want to find the area of the region between these two curves from some c to some d. So let's mark off c and d. There we are, c and d. So this is roughly what the region looks like. We can just fill it in like so. In this case, it would not be convenient to use vertical cross-sections. When you use vertical cross-sections, you need to know what the length of the vertical line is passing through the region. However, if I was to pick this x value over here and draw the vertical line passing through the region, it would be not very convenient because, as you can see, it passes through the region here and also here. So I would need to figure out what that length is for this piece, L1, and this piece for L2. And that's not necessarily going to be easy. However, if I instead do things for horizontal cross-sections, everything is much easier. So I'm going to pick some y value between C and D, say this one. And now I'm going to look at a horizontal cross-section. Since these are both functions of y, that means the horizontal lines will only pass through each curve once. It passes through on the left curve here and the right curve here. And what I need to do is I need to determine the length. Now the length is going to depend on y, because if I choose a different y, I'm going to have a different cross-sectional length. But how do we measure this length? Well, it's the distance between the 2 points. The 2 points have the same y value because this is a horizontal line. So the length here, the length of this segment, is going to be the difference between the two x values. The largest x value is f of y, and the smallest x value over here is given by g of y. So that's the length. So that tells me that the area is going to be equal to the lengths for each y going from C to D, dy. Again, dy is what you get because this length here is a small change in y. So the area is approximately the sum of a bunch of these things, Ly times delta y starting at C and ending at D. So this here is a length times a width. So this is the area of this small little very narrow rectangle, this horizontal rectangle. So L is the length, and delta y is the height. So you multiply those together to get the area of that narrow rectangle. And then you add them all together and that will give you the area of the region. Well, it's an approximate area. You need to take the limit as delta y goes to 0, and then that will become a definite integral from C to D, L of y, and the delta y becomes a dy. But this L of y here is just f of y minus g of y. And that's how we end up with the formula that we have.